This is the last lecture in the unit on patterns and growth. In the previous lecture, we began to think about a certain application of the mathematics we've been learning in this unit. Namely, we were thinking about models of population growth in biology. And we began to learn about three specific types of discrete population growth models. In fact, we've learned about two types out of three that we're going to study. We've learned about linear growth models and exponential growth models. So the starting point in this lecture will be to recall what we identified as a limitation of an exponential growth model. In the exponential growth model, remember there's a number r that we multiply by to get from one term in the population sequence to the next. And depending on whether that number r is greater than 1 or less than 1, there are two kinds of long-term behavior in the model. If r is greater than 1, then the population grows forever without any bound. And if the value of r is less than 1, then the population will die out. Now, the first behavior probably seems impossible, right? I mean, how could that be? That the population would grow forever without any bound. And so that leaves us the only realistic possibility, if an exponential growth model is a good model for all times, of having the population die out. So this is really a limitation. And based on this criticism, we're going to look at a third type of model. You see, the exponential growth model might be okay, even as a growth model, in a situation where the population size is relatively small and there's little competition for scarce resources. But in general, as we know, population is constrained by its habitat, that meaning its living environment. So let's try to bring that into our model in some way. And that leads us to this idea of a logistic growth model. Now, looking at the materials that you printed up before the lecture, I hope you will find a handout that looks like this. If you don't have it, make sure that you go and find it, because the next thing I'm going to do is I'm going to discuss that handout. I'm going to go away from the lecture slide somewhat. Well, here we are looking at the handout. It's called the logistic growth model. And just as we said, we're going to begin with an assumption that there is actually some fixed carrying capacity of the habitat. And then we'll make a second assumption, and that is that the growth factor of the population, the factor by which we multiply the population at a certain time to get the population at the next time, we're going to assume that that growth factor is proportional to the elbow room, by which we mean the difference between the carrying capacity and the current population. Okay, so we start at that point. We assume that there is a fixed capacity. You might think of it as an upper bound for the habitat, and then that the factor by which you grow is proportional to how much room there still is to grow. Now, the consequences of those assumptions are, first of all, that this growth factor, which we said was supposed to be proportional to the elbow room, must be, in fact, some constant times the elbow room. So the growth factor is a number r times c minus pn, where r is a constant that we're going to call the growth parameter. So what does the transition rule says? It says multiply the population at time n by this growth factor, and then you'll get the population at time n plus 1. So there's the transition rule. Population at time n plus 1, which is pn plus 1, is r times c minus pn times pn. So as a practical matter, what are you doing when you're calculating here? You're always multiplying three things together. The first one is the fixed growth parameter. The last one is the current population, and then the one in the middle is the elbow room, which of course really also depends on the current population. So let's see how that goes in an example. Suppose that the time interval that we're working with is 1 year. And suppose that the capacity that we're talking about is 1,000 organisms. Now, I've just made up what turns out to be a pretty convenient value for R, just as an example, and that is R equals 0.003. And now I'm just going to think about, what if the population is a certain value right now? What is it going to be next year? So I've done 4 different examples in this table. You want to look at this one row at a time. So start with the number 100. Suppose that right now, this year, the population is 100 organisms. Well, that's not very many, given that the capacity is 1,000, right? There's plenty of elbow room. In fact, the elbow room is 900. That's just 1,000 minus 100. So if I now take that elbow room and multiply by the value of R that I've specified, 0.003, I get a growth factor of R times C minus Pn, which is 2.70. Okay, 2.70. Now what is that? That's the amount by which you're going to multiply this year's population so as to get next year's population. That means next year's population will be 270. The population grew. Now, even before doing the multiplication, you should know that the population is going to grow. Why? Because the growth factor is bigger than 1, right? We're multiplying by something bigger than 1, so we're certainly going to make it bigger. Now, let's suppose that the population, instead of being 100, is 500. Let's suppose this year that the population is 500. So now I'm looking at the second row of that table. Then the elbow room is also 500. When you multiply by R, you get 1.50. So does that mean that the population next year will be larger or smaller? The answer is it will be larger, right? We're multiplying by something bigger than 1. In fact, it will be 750. Well, now let's suppose that the population this year is 900. So now we're doing a third example. We're doing the third row of the table. If the population is 900, that's pretty close to the capacity. The elbow room is only 100. When you multiply by the growth parameter, you get 0.30. Notice that is less than 1. And when you multiply by that, then you'll get a smaller population next year than you have now. The population, in fact, will be 300. And now the last example may show you something surprising. Suppose the population right now is 1,000. Okay? We have as many organisms as we possibly can. Well, what's the elbow room? The elbow room is 0. When we multiply by R, of course, we still get 0. That says the growth factor is 0. That tells us the population next year will be 0. So in fact, having the population equal to the capacity is not very good, because that means next year everything dies. As I mentioned below that table, that if the population happens to be greater than a certain number, 667, then next year the population will actually decline. Whereas if the population is less than that magic number, 667, then in the next year it will grow. Now what I'd really like to do is not just to specify individual populations this year and calculate what happens next year and just do that for 1 year. Let's actually specify a P0, an initial population, and generate a whole sequence of values for year 1, year 2, year 3, and so on. That's what I'm doing on the next page of the handout, so let's go forward to that. So to continue with the same example, so I'm using really the same assumptions. I'm assuming 1,000 organisms. I'm assuming R equals 0.003. And let's suppose that we start with 500 organisms. Well, we've already done that in the table. We saw that if the population at time 0 was 500, then to get the population next year, you have to multiply by 1.5. That will give 750. Now, take that value and use it as a population. Since 750 is greater than 667, we know that the growth factor is going to be less than 1. It'll, in fact, be 0.75. So the population at the end of the second year will actually be smaller than it was at the end of the first year. It'll be about 563. Now, I won't go through all the details of every multiplication for the rest of it, but the point is you just keep sticking that number back into the recursive formula, and you get the values P3 is 738, and P4 is 580, and P5 is 731, and so on. Now maybe you can look at this sequence of numbers and discern a pattern, but I recommend, as always, if you really want to understand what's going on, make a plot of your sequence. And here it is. Here's a plot of the population sequence over the first 20 years. And it's interesting to note that the population is seesawing back and forth. First it goes up, then it goes down, then it goes up, then it goes down, then it goes up, then it goes down. What is maybe not so clear, but it would be clearer if we took this out to an even greater number of years, is that those larger population values are declining. The lower population values are going upward, and in fact they're both approaching the same value. They both happen to be approaching what I've already identified as a special value in this model, namely 667. That happens to be the equilibrium value. So I claim as we take this model further and further forward in the future, we'll see the population alternately rising and declining, but getting really closer and closer to an equilibrium value of 667. All right, so we've seen how the logistic growth model works. I hope we see how the calculation is supposed to go. What we'd like to explore in the rest of this lecture is what kind of possible behaviors, what kind of pictures and plots are we going to see if we work with logistic growth models. And it turns out that compared to the previous two types of models, the linear growth models and the exponential growth models, this is a far richer situation. There are many more possibilities. And I want to emphasize that as I show you various possibilities coming up here, there's only one thing I'm changing in the whole model. So I'm always going to assume that the carrying capacity is 1,000. I'm always going to assume that the initial population is 500. And the only thing I'm going to change as I go from one example to another here is the value of the growth parameter R. So in this first example, I've taken the growth parameter to be the value 0.0009. And using that, I have generated a population sequence. As you can imagine, it would probably be convenient not to have to do these things by hand. And indeed, I used a simple spreadsheet to generate this population sequence. But I'm just following the simple rule where at each stage I'm multiplying three numbers together, one of which is always the growth parameter. And using this particular choice of growth parameter, you see what happens is the population dies out. You see it starts at 500, immediately it goes down to 225, it declines even further, and just look at the plot. This looks a lot like exponential decay. Despite the fact that we're using a logistic growth model, somehow the picture looks an awful lot just like what we saw in a model of exponential decay. The population is dying out. In my next example, I'm going to again stick with carrying capacity 1,000, initial population P0 of 500, and also it still will be a logistic growth model. The only thing I'm changing is the growth parameter, and here I take it to be 0.0015. So you can see at the beginning the population jumps down quite a bit, and after that it doesn't change very much. It has a little bit of decline at the beginning, and then it seems as if it's quickly settling down towards a single non-zero limiting value, which seems to be about 333. So it's similar to the previous one, except here the decline was to 0, and here it seems to quickly decline towards some other equilibrium value, not 0. All right, what else may happen? Well, let me try R equals 0.00315. And here, wow. So the population jumps up and then down and up and down. And very quickly, it seems like the values you're getting are almost the same. In fact, when they're rounded off, they do appear to be the same. Now, there may be a little bit of variation in the numbers in decimal places that have been rounded off or suppressed. But very quickly, the population sequence tends toward this periodic pattern with period 2. This is something that can happen with a logistic growth model. This could never happen in a linear growth model. This could never happen in an exponential growth model. Okay, how about if we go to r equals 0.0035? Well, what seems to happen almost from the very beginning is that the population sequence is going through a periodic pattern with period now 4. You can see the period of 4 if you try to look for horizontal lines that you could put through the dots, and you'll notice there seem to be 4 different heights. If I can use the terminology of singing, it's as if we have this pattern of voices, and it's just constantly going as follows: tenor, soprano, bass, alto, tenor, soprano, bass, alto, repeating forever in that same pattern of 4. All right, one more. Again, same carrying capacity, same initial population. I now take the growth parameter to be 0.0037. You'll note, by the way, that doesn't look very much different from the previous one. Here was 0.0035, and here I've gone to 0.0037. And wow, there doesn't seem to be anything that we would describe as periodic behavior. We may seem to see something that seems to repeat, but then the repetition doesn't continue. The only thing one can say in circumstances like this is that the population sequence seems to be chaotic and unpredictable. And indeed, we're really on the verge of a very interesting and modern subject in mathematics and science, which is called chaotic dynamics, or chaos theory. You may have read about this in popular accounts. Now, we can't go much further with this, but if we were to continue this subject, this would be a very interesting direction to go into the study of chaos. Now, another thing I want to study in these models is what's called sensitivity to initial conditions. Part of the process of mathematical modeling is to ask what happens as we make changes to the model. For example, if we change the model in some way, how does that change our prediction of the behavior that we're studying? Maybe we could make changes to the model so as to make it fit the real data more accurately. Now, in the logistic model, there are 3 values that we call parameters. That is to say, things that can be specified when we're making the model. There's first of all the carrying capacity, which we've called C. There's secondly this number that we've denoted by R, which we call the growth parameter. And finally, there's the initial population, P0. If we know those 3 numbers, we know exactly what mathematical model we have. What I'd like to do is to say, well, what happens when we change one of these values? And here's what I'd like to do. I would like to keep the carrying capacity fixed, and I'd like to keep the R fixed, and I just want to change the initial population, okay? We can think about changing other things, but let's not. Let's just think about keeping the carrying capacity fixed and keeping the growth parameter fixed, and let's just change this initial population. Now, why would a researcher want to do this? Well, maybe they think that they've got an accurate model. They have some theoretical or other reasons, maybe reasons based on evidence or other people's study, that the model is a good idea. The logistic growth model is a good idea. And what they feel uncertain about is the initial condition. They're not sure that they actually did their measurement correctly at the very beginning. Okay, so maybe they were out studying the lions in Africa, and for some reason they weren't able to get a very accurate count at the beginning. And they're wondering, well, how does that change the predictions made in the model? Well, we're going to look at 2 examples. In this example, we're assuming that the carrying capacity is 30 organisms, and we're supposing that the growth parameter is 0.1050. Those particular values don't matter. The point is, we're fixing the carrying capacity, we're fixing the growth parameter. And we're going to think about 2 possible initial populations. It could be 18, let's say, or it could be 14.5. Okay, so the first one we'll call A, the second one we'll call B, and in the plot I'm going to show one sequence in red and the other sequence in green. So I've plotted the red population sequence and the green population sequence. In fact, as you look to see the plot of the red population sequence, you'll say, where is it? Well, in fact, Over on the right, it's hidden underneath the green one. That's how much they agree. And what's kind of interesting here is that even though the population sequences have different initial values, right? One is 18, the other is 14.5. Very soon, as you use this model, the population sequences become indistinguishable. Wow. Another way to think about what we're doing here is, rather than think there's two different populations, let's think there's just one population, okay? There's actually one population out in the field, and let's say that's the red sequence, and the green sequence is another sequence that we've generated using our model, just sitting at our desk. But we just happened to put some inaccurate information in at the beginning, right? So we put in 14.5 when actually there were 18 out in the field, okay? Well, it turns out, in terms of making predictions, it doesn't matter, okay? Despite the fact that we were somewhat off with what we said the initial population was, very soon the predictions we're making, that is to say, using the green sequence, are virtually indistinguishable from what's actually happening with the red sequence. Of course, that's assuming that the population model is really valid. Okay, but what's interesting is, in this situation, the model makes good predictions in the long term. At the beginning, the predictions aren't so good, but they actually get better. Now, here for contrast is a different example. Again, I'm assuming the carrying capacity is 30 organisms, but this time I'm assuming the growth parameter is 0.1240. And suppose that we apply the calculations of this model with two different initial populations. Not so far off, but suppose A is 15.0 and B is 14.5. Well, at first, the population sequences seem to be very close to each other. If we look at the left side of this chart, the red and the green dots are almost indistinguishable out to about time, about 13, perhaps? And then all of a sudden, they go way out of whack with each other. They're just nothing alike. At time 21, they're very different. Again, it may be helpful to think not that we have two different populations, but that we have an actual population and a predicted population. And let's just assume that our initial population value, our P0, is just slightly off. Instead of being the actual 15, it was 14.5. So, is the model any good at making predictions despite the fact that we use incorrect initial data? Well, the answer is it's okay for a while. You see, the predictions made in green are very close to the actual values in red until you reach a certain point, at which time they just go completely kerflooey. They're just no good. But it still makes accurate and good predictions in the short term. It's in the long term that the predictions become wildly wrong. Now, it's interesting to see, if you contrast these two examples, here we had an example where having an incorrect initial value meant that the predictions weren't so good at the beginning, but they got better in the long term. Whereas in our second example, the predictions were pretty good at first, and then they became wildly wrong in the long term.